All right, everyone. So let's start our first lecture. So this is on electric charge and electric field. So in this chapter, we're going to learn about what electricity is. So what makes object electrically charged and what is a charge? What type of charges do we have? And then we're going to look at what we call Coulomb's law. Coulomb's law describes what happens between two charged particles. We're going to see that there is a force, a new type of force, electric force, between two particles or two objects that are electrically charged. And we're going to look at some applications of the Coulomb's law. Then we're going to look at what we call electric field, which is kind of analogous to the gravitational field that we studied in physics 6. And obviously, we're going to be learning how to solve problems, with electric forces. That means it's important that you guys review basically a vector addition, right? So how to add two vectors together. Remember, vector are quantities that have both magnitude and direction. And when you're adding them together, is not as straightforward as it might seem in the beginning. So if you have two vectors or three vectors and they're in two-dimensional, right, in different directions, adding them together requires a process. And I'm gonna give you some examples of that. So I'm going to show you a few examples, but it's a good idea to review what vectors are, properties of vector additions and things like that before going through this chapter. All right, so in terms of then electricity, right? So this Physics 7 class gives you introduction to a branch of physics we call electromagnetism. So we're going to start with electricity. We're going to learn everything about electricity. So the next 3 chapters are pretty much deals with, electric charge, electric force, and all of those, interaction between charged particles. Then after that, we're going to learn about magnetism. And we're going to have like 2-3 chapters on magnetism. And after that, the last chapter that kind of goes with, with the sequence, sort of like, let's say, puts those two together. So right now, electricity and magnetism doesn't, we don't consider them to be separate entities. So it's like electricity and magnetism are, always together. So that's why it's electromagnetism. So, but we kind of simplify by separating them and then studying separately, and then at the end putting them together. The last portion of the class is, basically goes over what we call optics. So optics, right, is the branch of physics that deals with interaction of light with, let's say, different surfaces. Maybe a surface that reflects everything, and it could be a surface that refracts things. So basically like mirrors and lenses and things like that. All right, so let's look at then in terms of this electricity, magnetism, and some of the historical facts about that. So everything around you right now, including the, let's say the device that you're using to watch this video, uses the concept of electricity and magnetism. All the cell phones and TVs and cars and everything, right? Basically powered by some kind of electrical device, electric motor or electric, some kind of, let's say, a device that converts electricity, like we call them transformers and things like that, right? So all of those use this concept of electricity and magnetism. And generally, one of the things we're going to see here is, apart from the gravitational force that we studied in physics 6, almost all the other forces technically have electrical, right, as a fundamental, property. That means when you push, when you pull, you are basically dealing with electric interaction between the molecules of, let's say, your hand and the object. That means those are the electric forces that actually, push and pull. When the friction acts on the object, well, the friction here is when the molecules of the box and the floor, right, they interact with one another, and friction is basically how strong the molecular bond between those molecules and those atoms are. So that means everything has some kind of electrical in nature. But, in terms of the electricity or magnetism, those phenomena has been observed thousands of years ago. So you can see, right, I give you some facts over here. So Chinese, for example, documented, the magnetism, as early as 2000 BC. And ancient Greeks, right, observed electrical and magnetic phenomena as early as about 700 BC. Or, we have documents, in terms of there are some of those observations. Obviously, what we're going to be learning in this chapter is not exactly what they have, thought of what electricity or magnetism are, but still, they were able to see some of those phenomena. That means, let's say, for example, if you take amber, you rub it with the fur, right? Then it can actually attract things. So that's why technically what we have here is amber, right? Is, what we use, the electricity, right? Comes from, that word amber. And also the magnetism, right? So it also has roots in ancient Greeks. The first rocks that have been, let's say, discovered to have the magnetic phenomenon have been near Greek city Magnesia. So that's why the name magnetism, right? Magnet come from that. All right. So we have to wait until about 16, 1700s for some of the natural philosophers to actually go a little bit deeper in terms of understanding the, let's say, fundamental electricity and magnetism phenomena, let's say the interactions. So you can see, right, William Gilbert in 1600 showed that electrification effects were not confined to just amber. Amber is very good at, if you rub it with the fur, it, you can clearly see the, effect on other objects, but, you can technically charge any object. You just, have to use the proper tool for that. So that means in around 1600, this discovery that not only amber, but all, other objects can also be electrified, made that, concept a little more general. That means others, natural philosophers could, try to find what are the, underlying effects, what are the, let's say forces or whatever, let's say that interaction brings back, right? So let's say, what are those forces, what are the interaction properties? And we have Charles Coulomb and Hans Oersted did, very important discoveries for us that, we will be, studying in the next several chapters. So in this chapter already, we're going to look at some of the Charles Coulomb's discoveries, where he was able to, experimentally verify that there is a force between two objects, two charged objects, and that force, we call it, like, let's say Coulomb's force sometimes, because he discovered that electric force. So that force is actually inverse square law, sort of similar to the gravitational, force, which also was an inverse square law. Then we have Hans Oersted, which by accident discovered that, let's say, magnetic compass. Remember, compass has a magnetic needle, which this, detects Earth's magnetic field. He discovered that, if you have an electric circuit, you can, deflect the compass needle with electric circuit, even though technically electric circuit is not considered to be a magnetic source, but, or they didn't know about that, it was a magnetic source. He was able to discover that technically, if you have electricity running in a wire, it can actually act like a source of magnetism and, deflect the compass needle. So it was a huge discovery. We'll talk about that later on in chapter 20. By the way, I am going, with respect to my lecture notes, in terms of this is, being chapter 17. So, and then we're going to talk about some of the other discoveries, like, let's say, like Michael Faraday and Joseph Henry, who then showed that you can generate magnetism from electricity, or you can generate electricity for magnetism. So that's why, once you understand electricity and magnetism, then we can study, let's say, what it takes to, unite them sort of like in one branch in terms of like unified electricity and magnetism. Obviously, since physics is experimental science, we're going to look at some of the experiments that were done to, let's say, verify some of those things. For example, Heinrich Hertz was able to verify James Clerk Maxwell prediction that electromagnetism is the reason that, let's say, the light is able to propagate in empty space. So he was able to unite electricity and magnetism and actually show that, for example, that light is an electromagnetic wave. We knew that light is a wave, but they didn't understand what type of wave. And, we're going to talk about that light is an electromagnetic wave. And for example, Heinrich Hertz, did experiment where he experimentally verified Maxwell's prediction. And hopefully you might be recognizing the name Hertz at this point, because we use Hertz for the frequency unit. Okay, so Hertz is for the frequency, exactly, you know, after Henry Hertz. Okay, so in any case, so we're going to look at some of this. So these are kind of like the historical background, and obviously, you know, in this chapter we're going to be going much, you know, deeper in our, you know, trying to understand the electric, let's say, what is electric charge, what is an electric, you know, interaction, what is electric force, electric fields, and all of the pretty much fundamental concepts related to electricity. All right. So to start with, we're gonna look at some simple experiments. So these are some simple experiments where these experiments were done. You can think of like, you know, by likes of, you know, Coulomb, to discover the effects of, let's say, electrically charged object on neutral objects or other electrically charged objects and things like that. All right, so you can see that here we have an experiment where we take two plastic rods. All right, so two plastic rods are basically, to start with, right, we can consider them to be what we call neutral. So neutral means that this object, right, in this case, for example, plastic rod, is composed of some stuff, okay, composed of some stuff. All right, so obviously at this point, what we have here is you can think of, like, let's say that stuff, you know, yes, we're going to talk about them in terms of protons and electrons, right? But think of like there are, you know, two types of stuff that we can have. So for example, if here's a rod, okay, so we can think of, like, let's say there are stuff that we can call positive, and another stuff we can call, let's say, negative. Okay, that means, for example, this plastic rod have, you know, some positive stuff and some negative stuff. If this plastic rod happen to have exactly same amount of positive and negative stuff, let's say in this case, I'm simplifying and saying, let's say 3 and 3, then those positive and negative, each one will cancel each other effect, and this object can be considered as electrically neutral. Okay, so it is electrically neutral. So then what we have here is things like this. So this first picture over here demonstrates what happens if you bring two plastic rods close to one another, but both of them are electrically neutral. That means, for example, both of them have equal amount of positive and negative stuff. Okay, so we call this pretty much electrostatics. That means, you know, they have, you know, equal amount of stuff. All right, so any two objects that electrically neutral, they have no effect, no electric effect on one another. But for example, if I bring those two together, hopefully, if you studied in physics 6, the gravitational force, where the gravitational force, if you remember, this is the equation between two objects that have mass. So let's say this is M1, this is M2. So any two objects that have mass technically attract each other gravitationally. So in this equation, gravitational force equals to G, the constant, times product of mass 1 and mass 2, and then divided by their separation square. Okay, so hopefully you guys have seen this equation from physics 6. This equation is the magnitude of the gravitational force between two objects. Now, if I bring those two objects close to one another, I can theoretically calculate their gravitational force, their effect on one another, but you will never see any effect because this gravitational force is very, very weak between two small objects like that. You need to have, like, let's say, Earth, Sun size objects, right? Very massive in order for this force actually to be, you know, visible, the effect of this force to be visible. But look at this force. One of the interesting thing about this force here is this. Remember, the mass is intrinsic property of object, okay? So, and this force is a constant, we call it gravitational constant, G, times then the product of those intrinsic properties of mass 1 and mass 2. So that means product of those two properties, then divided by their separation square. So this is what we call inverse square law. Gravitational force is inverse square law because it's proportional to their distance square. Closer they are, stronger the effect. Still, those objects have a very small mass for any type of effect for us to be visible from that point of view in terms of gravitational force. But what we're going to do here is this. Same thing, we're not going to see any effect if those two objects are electrically neutral. But what we're going to do here is we're going to make them charged. Okay. To do that, we're going to take the plastic rod, then we're going to take a fur, and then we're going to rub the plastic rod with a fur. Okay. Now think like this. So here's a fur, and you rub it, and remember, we start with the plastic rod, which is neutral, and the fur, which is also, let's say, neutral. Okay. Now, what I have here is this. I take neutral plastic rod, neutral fur, and then I rub the rod with the fur. Okay. After that, we do that same for the second rod. And then when we repeat the experiment, what we'll notice here is this. You bring the second rod closer to the first rod will actually be moved. It will be sort of like pushed. See, this means it is kind of pushed. See, they're not actually touching each other. So, but there's some kind of like a push that acting on rod, rod 1, let's say. This is rod 1, this is rod 2. Okay. And this happens after we rub the plastic with the fur. Now, what happens here is during that process of rubbing the plastic rod with the fur, we are charging the plastic rod. Now, what do we mean by charging? So here's what happens. When we do the rubbing, right? So let's say looking at this scenario, right? So when you do that, some of the stuff from one object is then moving to another object. That means we have two objects there. We have the rod and the fur. And usually when you're rubbing, that interaction allows some of that stuff to be able to go from one object to another. Now, what happens here is this. This negative stuff from the fur goes to the rod. And let's say then this negative stuff goes to the rod. And let's say that negative stuff goes to the rod. Now the rod has 6 negatives and 3 positives. What happens here is those cancel, those cancel, those cancel, but then let's say end up with some extra negative stuff that don't get canceled in the rod. That means then you can see, right, the rod becomes more negative than positive. And you can see, right, those 4 lines represent, or 5, sorry, those 5 lines represent 5 negative stuff. And you can think of right now that those 5 represent the extra negative stuff that the rod has. That means I'm not putting all the, stuff that it has. So this means those are extra stuff that it has, and those extra stuff are negative stuff. That means it's 5 extra negative stuff than positive stuff. Same thing is here. If I take the plastic rod and rub it with the fur, some of the negative stuff from the fur goes into the plastic rod, and now both of those plastic rods have extra negative stuff. And when I bring them together, what happens here is I can see that they are repelling each other. All right, so they're kind of pushed apart. That means if you bring 2 objects that have the same stuff, that means they have same, let's say negative stuff in this case, they are actually, repel one another. Okay. Now, let's do another experiment. This time with the, glass rod. We start again with a neutral, 2 neutral glass rods. Remember, again, neutral means that they have equal amount of stuff, right? Plus, 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 minus, minus, minus. So here I'm doing their, equal amount. So they're neutral, so they have no electric interaction. Then what we do here is for this particular combination for glass rod, what works best is the silk. So we take silk, and we rub the glass with silk. Okay. Again, so you take the glass, plus, 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 let's say minus, 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 and then let's say this is the silk. Also, same combination, it's neutral, and then you rub it. But what happens this time is this. This interaction, right, makes then negative from the glass to go to the silk. This negative goes to the silk, this negative goes to the silk. That means now silk has 1, 2, 3 extra, negatives, but the glass has, 3 less negatives, right? So that means it becomes more positive than negative. So then we can see that, right? It becomes what we call positively charged. Same thing we do with the second rod. Then we bring them together, two positively charged rods. And again, what we see here is that they repel each other, right? So that means if you have negative and let's say another negative, negatives then repel each other. If you bring positive with another positive, again, they repel each other. Okay, that's kind of what we have, seen up to this point, right? So that means your two negatives repel, two positives repel. What if you bring positive and negative together? Let's say I have the, negatively charged plastic rod, positively charged glass rod, bring them together. What we see here, they are then attracted to one another. Okay, there's an attractive pull between them because they have opposite charges. Okay, so remember when I do the rubbing, right, in terms of the silk and the fur, remember the charges move from one to another. That means after that, silk also charged. Remember, if I go back, see the silk gets, so if I kind of get rid of the ones that cancel each other, see the silk becomes negatively charged. And if I go here, I can see then if those three go from the fur into the plastic rod, now fur is positively charged. That means you can see that fur positively charged, technically it can then attract the negatively charged rod. Silk negatively charged, it can attract positively charged a glass rod. That means the experiment shows that you can charge an object by rubbing with the silk or fur, let's say. And then what you can do here is you can bring those two charged objects together, and any two charged objects together, right, can exert force on one another. They can repel or they can attract. And what we can see from here is like charges repel one another, unlike charges, attract one another. Okay, so that's kind of like the experiment that, have been done to kind of recognize that there are actually two charges and that those, I call it two stuff, right? That's basically two types of charges, positive, other one negative. And what we have here is Coulomb's then, right, was able to do experiments to see the force between them. But before that, let's look at kind of, if I go back here, look at just this each negative charge or this each positive charge. And let's say, how much charge are we talking about for the single positive or single negative? And is there a difference between them? Well, to answer that, there is no difference between them. So if something is a single negative or something is single positive, have exactly same charge. Sometimes we use E minus or E plus. E is for the electric charge, okay? And now what we're gonna say here is that negative here is gonna be called electron, positive one gonna be called proton. Proton. Now, then in terms of the charge, the magnitude of the charge for each one of them is 1.602 times 10 to the negative 19 Coulomb. So this is known as electric charge. And both electron and a proton have same electric charge. Now, one of the things we have here is this sentence here says that electric charge is quantized in the units of the electron charge. Okay, that means if you have an object, so this object is sort of like the integer number of those electric charges. See, the smallest single object you can have there is a charge is either one electron or one proton. How about another one? Well, the next one will be, let's say, 2 electrons or 2 protons. And you can see, right, and then 3 electrons. That means 1e or 3e, right? And or let's say 3e negative here is this one 3e positive, or then you can have, let's say 5, 6, let's say 6e negative. That means they go like, 1 electric charge, 2 electric charge, 10 electric charge, or n number of the electric charge. There is no such thing as 3/2 electric charge, or 5/2 electric charge, or thing like that. That means there's no fraction. That's why it's quantized in an integer number of electric charge. That means 1, 2, 5, 10, 1,000, 1 billion, but no, let's say 3.25 electric charge and thing like that. Also, we have here is the conservation of electric charge. Means that electric charge is conserved. Okay. That means, for example, if I have an object, let's say that plastic rod, right? So that we talked about. So, and remember, so let's say I have 3 electric charges, 3 positive and 3 negative, okay, for example. That means, the total here is, in terms of this, right? So let's say I have 6, electric charge, right? I mean, or let me, let's say they're technically they cancel each other, right? So there's not electrically charged, but, or let me do this like that, then maybe like this. So then you can see that this is 3 protons together. All right, so then, for example, I use then a silk, right? So I use the silk. And what I do here with silk is, remember the silk right now is neutral. So I'm not gonna put anything, so let's say it's neutral. So from now, whenever I put positive or negative, I'm gonna be representing the extra stuff that it has, extra charge. So let's say the silk is neutral. That means right now, since silk is neutral, so the charge of the silk, which we use Q for that, right? Charge of the silk is 0. Charge of the rod, sorry, not G, but Q, is 3 protons. That means the net charge is sum of those two, so 3 protons. Okay. Now, when I do the interaction, that means when I rub it with the silk, then some of the things I can have here is some of the negatives from here can go over there. Or maybe like some of them here can go over here. But the idea here is how much is moved from one to another, right? So let's say, for example, let's say this guy here goes from here to there. That means this doesn't have it, but this one has it. Well, then what I have here is I can then change then that this becomes 2, then this becomes 1. Then if I add them together, I'm still gonna get that. And if I continue, let's say this one, I'm gonna go from there to here. Then this becomes 1, this becomes 2. And again, if I add them together, I'm gonna get 3. That means no electric charge can be created or destroyed. During the interaction, they can go from one to another, but you cannot just create electron or a proton out of thin air. There's no such thing, okay? If you are charging something, if your object was neutral and now suddenly charged, that's because some other object that it was interacting with lost some of these charges or gained some of the charges from your object, so your object became charged. You put the sum of those two together, you're still gonna get same constant value. Okay. Now, so here we have sort of like the basic atomic, let's say, model that we usually use in chemistry or in some kind of science class. So we have atom consists of 3 particles, electron, proton, and neutron. So we have a nucleus, which is at the center of the atom, right? Is where the electron and the neutrons and protons basically. So you can see, right, the nucleus has positively charged particles, we call them protons, and then neutral particles, we call them neutrons. So those grays are neutron. Now, what I have here is, for this particular case, this atom has 3 protons and 4 neutrons. That means the charge of the nucleus, so the Q for the nucleus is 3, let's say E plus. Let me kind of do it like that. 3E plus. but then it's surrounded by the, what we call cloud of electrons. So you have 1, 2, and 3, right? That means it also has, let's say Q, I don't know, outside, let's say, is 3 electrons. Now, what is the net? Well, the net will be 0, right? Because I add those two together, you get 0. That means those are, neutral. That means this atom is neutral. Now, what it means here is this. I also have neutrons. How about those? Well, neutrons have no charge. That means, in terms of the charge, they're not contributing anything to the total charge. Okay. Doesn't mean that they are not contributing anything to the atom, right? One of the things you're going to see here is, each neutron is actually individually, they're slightly even heavier than a proton. That means, right now, having those 4 neutrons, you are basically have, extra mass added to your atom. Now, in terms of then what we have here is the charge is 0. That means this atom is neutral. Okay. So again, coming back to that, so you can say, right, neutral means that here's the nucleus with 3 positives and 3 negatives. So you can write 3 protons, 3 electrons, 4 neutrons, and 0 net charge. Okay, so this is known as a neutral atom. Well, one thing we can do here is then we can charge it. Charge means that you have unequal amount of electrons and protons. That means either, more protons and, less electrons, or other way around. Now, in terms of then how we charge the object, it's kind of like similar to those experiments. We interacted with some kind of object like, silk or fur. But the way we then charge it, for example, here, so you can see, right, in this case, we have the nucleus with 3 positives, but then we have only 2 negatives. That means 3 protons, 2 electrons, which means then this charged object, this particle, right, is now charged because it has 3 protons and 2 electrons. So if I add them together, I'm going to get basically 1 positive electron. So we call this positive ion. That means this is the net charge. Well, one of the things we did here is then we basically made the number of electrons and protons different, and that made the object charged. So this one is positively charged. Same way, we can look at it in terms of, okay, here's the nucleus with 1, 2, 3. And now we have 4, electrons. That means I can have here is, 3 protons, 4 electrons. And now my net charge will be, 1 extra electron. Okay, so this one is known as a negative ion. Okay. All right, so that means important thing here is this. To make this object, neutral object, as a positive ion, I removed the electron. Remember, so there was 1 electron, so I removed that from the atom. To make the neutral object a negative ion, I gave it an extra electron. Okay. So the important thing here is to realize that I didn't do anything to the nucleus. I did not change number of protons. It was 3 protons the entire time. And if you remember your periodic table, 3 proton is lithium. So lithium has 3 protons in the nucleus. And when I'm charging it by either removing electrons or adding electrons. I never charge it by removing protons. Because if I remove protons, first of all, it's not lithium anymore, right? If I remove a proton, hopefully you can, again, if you remember your periodic table, it's helium. 2 protons, helium. I remove 1 more, becomes hydrogen, right? So you're changing the property of the atom itself by changing the number of protons. Becomes different element at all, right? So changing the number of electrons doesn't change the element. It just makes it, ionizes it, right? Makes it an ion. That means every time there is electric interaction, that electric interaction is due to the fact that electrons, never protons, but electrons are free to move from one object to another. Some objects have, we call them conductors, right? They have lots of those free electrons, lots of those electrons that can be moved from one object to another. They call it valence electron. They can be shared and things like that. But generally, remember, the nucleus is at the center. Those protons are very close to one another. There's a very strong molecular bond between them. So it's very difficult to actually take out some of the protons. Doesn't mean that it's not possible, right? We can still do that, right? So basically, there's decay, right? When you remove an electron, you just basically you're decaying it, right, to something else. But that's a completely different process, and we don't want that. All right, so the protons and electrons have the same magnitude of charge, kind of summarize. The magnitude of charge of the electron or proton is a natural unit of charge. Natural unit means that there are three natural or fundamental units that we studied in physics 6, kilogram for the mass, meter for the length, and seconds for the time. Those were natural or fundamental units, okay? So that means the mass, length, and time, not fundamental or natural units. Charge is one of those. That's the fourth one. That means the charge is another fundamental unit. And again, what we get here is, remember that charge is, quantized, okay? And we have this principle of charge conservation that states that algebraic sum of all the electric charges in any closed system is constant. All right, so there are other experiments we can do in terms of, charging an object. So these are some kind of like application that we can look at. So let's look at, for example, a metal ball. So here we start with some metal ball, which is what we call a conductor. Remember in physics 6, you learn about conductors, in terms of conducting heat rather than electricity. So conductors have, are types of objects, right? The type of material they have there, allows the heat propagate very easily. Same thing with electricity. Conductors are good at conducting electricity and heat and sound and things like that. So metals are the best conductors. And for example, you also have what we call insulators. For example, you can see, right, nylon thread that we use to hang the ball is insulator. That means the charges will not be moving through the insulator. Charges can move from one object to another through the conducting, wire or conducting, let's say rod and things like that, but not through the, let's say, insulating rod. So that's why, for example, here you have, let's say this is earth. And see, this is a metal conductor. And this is a metal conductor. But this guy here is an insulator. That means electrically, a ball and, let's say this rod here, right? They are isolated from one another. All right, so let's say you can see that what I'm gonna do here is I'm gonna bring a charged plastic rod and I'm gonna connect the charged plastic rod, negatively charged, to the metal ball with another conductor. This copper wire is a good conductor, so that I'm connecting those two together. What happens here is that charges will go from one object to another. In this case, for example, this negative can go from, a rod to the ball. This negative gonna go from rod to the ball. Doesn't mean that all the negative charges go from charged plastic rod to the ball, but at least even if some of them go, now metal ball has more negative than positive, so then it becomes charged. So you can see, right? Even if it just receives a little bit of negative stuff from the rod, if I remove that copper wire, right, copper rod, and bring those two together now, they're gonna repel each other because we were able to charge, right, charge the ball by physically, right, using it, the copper, copper conductor, we physically connected those two. So this is known as charging by conduction. That means we used a physical object between two, let's say two different objects, right? The third object is physically touching those two, and there's a flow of charges. So that means if I bring a positive charge rod, glass rod now, then the metal ball will be attracted to the charged glass rod, because remember, ball was negative, charged glass rod is positive, so then can be then, attracted to one another. All right, so here's another experiment that we can do. Again, we have a neutral, right? So this is neutral. So you have a neutral ball, a metal ball, and it's a good conductor, and it's connected to Earth. So basically, Earth is also very nice place for the charged particles. They always try to escape to Earth. But we use an insulator there. That means the ball will be kind of like disconnected, right? It's not connected to Earth because there's an insulating stand. Now, what we're gonna do here is this. I'm gonna bring another negatively charged rod. Okay. Remember, right now, this ball here has sort of like equal amount of, all right, that's not what I intended to do. So let's say equal amount of positive and negative. Okay, and they're kind of like randomly, distributed. So like that. All right, so what I'm gonna do here is I'm gonna bring a negatively charged rod, and I'm not gonna touch the metal ball. I'm just gonna, bring it close, but not really physically touch those two. But what happens here is this, because this is negative, all those positives that we have, all the positive charges in the metal ball are going to be attracted toward that negatively charged rod. So they're going to move as close as they can to the rod. Obviously, they cannot jump from the ball, but they can, accumulate at this end. All the negative ones in the ball will be repelled by the charged rod. So they're gonna be pushed as far as they can, which is now they're accumulated at this end. So what we do here is we separate those. You can see, right? We separate those charges inside the ball. Inside the metal ball, we have left side is all positive, right side is all negative, because negatives have nowhere else to go. That's the furthest they can be pushed by the rod. What we're gonna do next is this. We're gonna use a wire to connect. So that means over here, right? If I go back, so think like this. I put a wire here and connect this to Earth. That means I'm giving path for those electrons to escape the ball to Earth, and they're gonna take it. All of them gonna then move through that, a rod that I connect to that wire to Earth, to ground, what we call ground. Now the ground become negatively charged in this case because it receives those, but the ground is so big, that means, and the difference, of only like few negative charges gonna make almost no difference for that. So it's very, very, very tiny charge for the ground. But metal ball now lost all of those electrons. That means it has more positive stuff than negative stuff. That means there's more protons than electrons. And this is known that at this point, right, we charged the metal ball. So this is known as charging by induction. So charging by induction. Right, so charging by induction. All right, so that means our goal was to remove some of the electrons from the metal ball, and we did that by first separating them, then using a wire to connect the ball to ground. Okay. Another thing we can do here is this, and this is actually an experiment that even you can do. So take any plastic object around you and try to find something, I don't know, that has maybe like, let's say a fur, right? And if you don't find any fur around you, try to use your hair. So rub it, basically take the plastic, let's say a pen, right? And rub it, with your hair. And then have some small pieces of paper, right? So if you use some small pieces of paper, so first rub the pen with your hair, and then bring it close to that piece of paper. And then you can see that you will be able to pick up those small pieces of paper, okay? So this is possible, even though those small pieces of paper, technically they're neutral. So they're neutral. Then how can you pick up something that is neutral? Even if you, let's say, charge your comb or charge your, let's say, a pen, right? Well, what happens here is this. So when you charge your comb, in this case, right, by let's say rubbing to your hair, and you bring it to the paper, right? So let's say some small piece of paper that you have in front of you. What it does here is it polarizes, all the atoms inside your paper, inside that neutral paper, where all the positive ones are attracted, all the negative ones are repelled. But eventually, because all the positive ones, so think like this. So let's say here's a piece of paper, and let's say this is your object. See, your object is negatively charged. That means all the positive object. So let's say all the positive, sorry. All the positive will be attracted and move toward the rod, and all the negative will be repelled and moved away. And what happens here, there's a force, attractive force, right? On these positive charges, but there's also repulsive force on those negative charges. But what happens here is because those positive charges are closer to the, let's say electrically charged object, in this case, like let's say your charged comb, because these guys are closer than the negative ones, the net effect is end up being this, and this is stronger, so attractive force wins, and then you're able to pick up the pieces of paper. Now, how about if I have a positively charged object instead of negatively? That means this guy instead of negatively charged, how about it is positively charged? What do you guys think? So think about it for a minute. Let's say you can pause, think about it, and then continue, with the video. Well, you're gonna get the same thing actually, even if it's positively charged. So what's gonna happen here is, let's say here's your paper, here's your object, and let's say this is positively charged. So now it's gonna attract all the negative ones and repel all the positive ones. You still have an attractive force, you still have a repulsive force. But because those are closer to the object, to the charged object, attractive force is stronger than repulsive force, and your object going to be attracted to the positively charged comb. Okay, that means what you get here is basically the same thing, even if you have a different charged object. All right, so then let's look at an experiment that was done by Coulomb. So Coulomb did an experiment where he was trying to find the relationship between two charged particles. That means, what type of force they exert on one another. And what is that force depends on? Does it depend on their charge? Does it depend on their, let's say, distance between them and things like that? Or if they do, how does the force can be expressed? So one of the things you can do, right, you can see, right, he basically did an experiment where, he used two charged particles and he moved those two closer together. And there's a torsion over here there with the sort of like, let's say, a spring that he was able to rotate and be able to find, let's say, you bring two charged particles closer together, they are pushed from one another, but then, you used same amount of force to bring them back to their original spot, and how much force it takes to bring them back is exactly equals to basically the electric force that they exert on one another. And this force is known as the Coulomb force, was then, let's say, he was able to, let's say, then to show that this force directly proportional to the product of the charge of object 1 and object 2, or charge 1, charge 2. So let's say if you have two charges, here's charge 1, here's charge 2, and let's say those charges are separated by this distance r. R is not their radius, not their size, but the separation between them. There's a distance between them. So then this force is proportional to the product of those charges. That means the Q1 times Q2. Okay. Then he was able to discover that means, if you make the charges, if you double the charges, right? So let's say here you have 2 times Q1 and then 2 times Q2. So if you double in the charge, force is not doubled. Force actually becomes 4 times stronger because you have 2 times, 2 times. So that means it becomes 4 times. That's how he was able to see that the force depends on the product of their magnitude rather than, let's say, they're just their magnitude. So also he was able to, let's say, do an experiment where he was able to, see what is the relationship of this force to their distance. So let's say you have the distance r, and let's say if you double the distance between them, would then the force be half or double, let's say. And one of the things he noticed is that the force actually decreases if you move them apart, but it's, let's say, double the distance doesn't make the force becomes half. Actually, force becomes 1/4. You triple the distance, force becomes 1/9 of what it was before. That means it is proportional to the distance squared. So that's why it's an inverse square law. And then whenever you go from proportionality sign to equal sign, you then introduce a constant, and that constant is, well, let me put like K over here, right? So K, again, this is, this letter K is used a lot in physics. So we have as a spring constant, we have thermal conductivity and things like that. Here, this is as electric constant. So sometimes I would just put E over there, KE, electric constant K. So then you don't get confused with the, I don't know, spring constant K, let's say. All right, so then this equation then is known as Coulomb's force equation. And this is for the magnitude. This is for the magnitude of those, of the forces between two objects. And one of the things we have here is then this force also happened to be example of Newton's third law. Okay, so try to remember what the Newton's third law, tells you. Newton's third law tells you that any two objects that are interacting with one another, that means two interacting objects, exert force on one another. And the force that they exert on one another has the same magnitude, but opposite direction. Remember those action-reaction forces? The Coulomb's force is an action-reaction force. See, here you have charge 1, here you have charge 2. If you bring charge 2 close to charge 1, then you exert force. So this force is the force that 2 exerts on 1. So that's why you can see, right? Notation here, 2 on 1. And here's the force that then 1 exerts on 2. So this is the force that 1 exerts on 2. Now, both of those forces have the same magnitude. That means in terms of magnitude, F21 equals to F12. Put it like that in terms of, like, let's say the magnitude. But then what I have here is, you can see right there in opposite direction. So that's why if I put it in a vector format, I can say that as vectors, they have the same magnitude, but that negative means that they're in opposite direction. And that's always, you're gonna get that. So here, the reason that, let's say, the force is in this direction, because it's repelled by the Q2. And the reason that force 1 is in this direction, 1 on 2, is because the 2 is repelled. And you can see, right, those two forces are in opposite directions. Okay, they have the same magnitude, and I can use this equation, right, to calculate the magnitude between those charges, but they have the opposite directions. What if I make one of the charges negative? Well, what I have here is then the direction of the forces change. That's because positive and negatives attract each other. If Q1 is, because, right, if Q1 here is negative and Q2 here is positive, see, they are separated by this distance r, then what we get here is this. Q1 is pulled toward Q2 because Q2 attracts it. Then this will be the force. This is the force 2 on 1. I usually put 2, 1. And then 2 is pulled toward Q1. So then this is the force that 1 exerts on 2. Okay. And I can use this equation, F21 equals to F12, and this is equals to K Q1 Q2 over their separation squared. And I can calculate the magnitude of the force. How about the direction of the force? Because remember, force is a vector. Well, it depends. See, if I'm considering charge 1, the force on charge 1 is to the right. If I'm considering charge 2, the force on charge 2 is to the left. Force on charge 1 is to the right. Force on charge 2 is to the left. That means as soon as I let them go, Q1 will be speeding up to the right, and Q2 will be speeding up to the left, because the forces are in opposite direction. They, and the objects, remember, they change their momentum, or they accelerate in the direction of the net force. All right, so hopefully, you're able to follow. Remember, you can always pause and go back and rewatch it again. So let's kind of summarize what we have. The object, when it has a charge, we can represent it with the Q. Q is the charge unit. So let's say Q is for the charge. But if we know that the charge of the particle is, let's say, 1 electron charge, that means we're dealing with just an electron or a proton. That means I can say that Q is equals to E, where E is the smallest unit of charge. Okay. By the way, here it says except for quarks. All right, so if you don't know, remember, so let's say if this was the atom, so let's say, so the atom, remember, have, let's say 2 electrons, or we talked about 3 electrons. Remember, this was the nucleus, right? So it had 1, 2, 3 protons, and let's say 1, 2, 3 neutrons inside the nucleus. And what we do here is we use those 3 particles as subatomic particles. That means you have electron, proton, and neutron. So let's say it like that. So we say that charge of this one is negative. So in a way, what I can say here is electron, E, has a charge of negative 1.602 times 10 to the negative 19. And then the proton has a charge of positive 1.602 times. Usually you don't have to remember those numbers. So 1.6 even is good enough. So I usually write 1.6. So this is what I write, 1.6 times 10 to the negative 19. All right, so then 1.6 times 10 to the negative 19. If it's an electron, we usually use negative for that. If it's a proton, we use positive for that. And if it's neutron, it's 0. Now, another very important thing that we're going to be using a lot is then the mass of those particles. 1 electron has a mass of, usually I write mass of the electron, right, as 9.1 times 10 to the negative 31 kilogram. And mass of the proton is then 1.67 times 10 to the negative 27 kilogram. All right, so hopefully you guys can see interesting fact here. Electron has the same charge as the proton. They have the same charge, but proton is almost 3,000 times heavier than electron. So this is the mass of the electron. So you can see, right, negative 31. This is 27. That's a factor of 1,000 and factor of actually about 3,000. Neutron has no charge, but it has mass. And it's actually a little bit even heavier than the proton. It's actually slightly heavier than the proton. But in terms of when you're considering electric charge, neutrons are basically useless to us because they have no electric charge. Now, the quarks are subatomic particles, are even smaller particles inside the proton and neutron. Technically, then, what we have, instead of using subatomic particles as electron, proton, and neutron, in particle physics, we use electron and quarks because every proton has 3 quarks inside. Every neutron has 3 quarks inside. And each quark has a different charge, and their combination charge is then basically gives this one plus E, and this one is 0. Okay, that means what we have here is we don't have to worry about quarks at all in this class, but you just know that a proton and a neutron are not fundamental charges. They are things inside them, where electron is a fundamental because there's nothing inside electron. All right, so those are the, this page is going to be, sort of like, let's say, something that you should be referring to quite a lot, because it has all the information, the charge and the mass and things like that. And in terms of then the charge, see, 1 Coulomb charge, by the way, the units for the charge is Coulomb, after, Charles Coulomb. 1 Coulomb of charge is a lot of charge. So you can see, right, you need 6.24 times 10 to the 18 electrons or protons for you to have just 1 Coulomb. So that's why a lot of times charge would be ranging, let's say, from 10 to the negative 6 Coulomb to, let's say, 10 to the negative, let's say, 11 Coulomb. That means this is micro to nano generally, and then this is pico. So micro Coulomb, nano Coulomb, pico Coulomb. So that's kind of like, what you might see. Sorry, this is 12. All right, so that means 10 to the negative 6, 10 to the negative 9, which is nano, and 10 to the negative 12 is pico. Okay, those are the typical values for the electric charge. Okay, so let's look at a couple of examples then. We have a glass rod that is charged to +5 nanocoulomb by rubbing. Now the question is, have electrons been removed from the rod or protons added? Well, think about it. So right now our charge, so how much charge we have here is +5 nanocoulomb. Remember, this means this rod has 5 nanocoulomb amount, right? That amount of extra positive charge. Remember, when we say object is charged, that Q represents the extra charge it has. So in this case, it has 5 nanocoulomb worth of extra charge. Remember, you charge it by rubbing, a rod, right? By, let's say in this case, would be a silk. Now, think about it. Is it because protons were added? Because that's why it's extra positive, or electron removed? Well, hopefully you were able to, figure out at this point that whenever you're charging something, that's because electrons are being removed or electrons are being added, never protons. In this case, you have, removed electrons. You removed electrons, so that's why it has less electrons. That means it has more protons, so more positive charge. Okay, so then how many electrons have been removed or protons added? Well, let's scratch that. There are no protons added. Let's look at how many electrons have been removed. Okay, so what we do here is this. So remember, so what we have here is we have 5 nanocoulomb worth of charge. Remember, the charge comes in quantized amount, right? That means it's some n number of charge that has each one a fundamental charge. That means it's n number of electrons, each one having an E charge. Let's say E is the amount of electric charge. That means you want to know here is that this N, which is the number of charges. Or if you want, you can use the, let's say, capital N, because usually capital N is used for the number of something. So the number of electrons in this case. All right, so then you can see, right, Q is equals to N times E, then N is equals to then Q over E. Well, our Q here is 5 nanocoulomb divided by E. Well, remember, one of the things we do here is this. Nano stands for 10 to the negative 9. So you actually have to write that 10 to the negative 9 coulomb divided by the fundamental charge. And that's 1.6 times 10 to the negative 19 coulomb. See, the coulomb cancels. So what you get here is some kind of number. All right. And what we're going to get here is 3.1 times 10 to the 10 electrons, let's say. All right. So, well, in a way we can say, right, this is roughly 31 times 10 to the 9, and this is billion, right? So that means 31 billion, electrons have been removed in order for this charge to be only 5 nanocoulomb. All right, so let's look at another example. Suppose you have 1 mole of oxygen gas. O2 gas. How many coulombs of positive charge are contained in the atomic nucleus of this gas? Right, so hopefully you guys remember, right, from physics 6, let's say if you just taken, probably it's fresh, but if you're not, maybe let's just review some of those things. So remember, 1 mole is, in a way, gives you a certain amount of, particles. So 1 mole is equal to what we call Avogadro number, right, of particles, which is 6.02 times 10 to the 23. So 23, let's say particles or molecules. So that means we are, when we're given this, right, we're basically told how much stuff we have, right? 1 mole of the gas, which means that many particles, molecules of O2 gas. All right, so now, oxygen comes with, so let's say the question is that how many coulombs of positive charge are contained in the atomic nuclei of this gas? All right, so oxygen, if you kind of, again, remember your periodic table or not, if you have something, that you can look up. So oxygen has 8 protons. But we have O2, which means times 2. That means O2 has 16 protons, right? So considering the oxygen molecule. All right, so now that means each nucleus, so let's say here's the nucleus of this O2, okay? So each one, let's say 1, 2, 3, 4, 5, so let's say, 16. All right. So it has 16 protons. So each one has 16 protons. That means I can write as 16 protons like that. Okay. All right. So that means each oxygen molecule has 16 protons. And how many oxygen molecules do we have? Well, we have 1 mole of it, right? Which means 6.02 times 10 to the 23 of those. Now, how much total charge we have? Then Q will be, all right, so we have 16 protons for each oxygen molecule, but then we have 1 mole of it. That means 6.02 times 10 to the 23 of those. And then we just, put them all together, because then what I can do here is this, it's 16. This is nothing but 1.6 times 10 to the negative 19 coulomb. Then times 6.02 times 10 to the 23. And then what we get here is 1.5 times 10 to the 6 coulomb. That means I get 1.5 times 10 to the 6 coulomb of charge. All right, so we have a lot of charge because we have a really large number of molecules, right? And that means we have a large number of molecules, and this is a molecule that has, a large number of protons in the nucleus. That means overall we get, 1.5 million, right, coulomb of charge, which is, insane amount of charge. All right, so another example here. So we have now ready to solve some problems involving Coulomb's force. So we're given 2 point charges. We have a point charge A is -1 nanocoulomb, and the point charge B is 4 nanocoulomb. That means what I can do here is I can do like, okay, so here's a charge A. And I know it's negative, so I can put just negative like that. So it's -1 nanocoulomb. And here's charge B. So it's positive, so I put plus. So charge B here is plus 4 nanocoulomb. They are separated then by 1 centimeters. That means I have then distance, R is equals to. Now, remember, the length for the force has to be in meters. So it's 0.01 meters. You have to make sure that to use, units of or MKS units if you want, like SI unit. MKS stands for meters, kilograms, seconds. Okay. So what I want to know is this: what are the magnitude and direction of the electric force on charges A and B? Okay. Now, one thing I have here is this: because those charges are opposite, unlike charges, right? Then what I'm going to get here is I'm going to get electric force that's going to be attractive. That means there's going to be force B on A to the right, and then force A on B to the left. And I can calculate the magnitude. Remember, those are action reaction. They are the same, force AB or force BA. And the equation for this is K times QA, QB divided by their separation square. All right, so one thing I forgot to mention is, what is the value of K, this electric constant? Well, the K has a value of 8.99 times 10 to the negative 9. But a lot of times, since it's 8.99, I wouldn't mind if you just write this as 9. Okay, so the units are newtons, meter square over coulomb square. So that's my constant K. Again, that means electric constant is, again, 9 or 8.99 times 10 to the negative 9 newtons meter square plus coulomb square. Okay, then this is divided by their separation square. That means 0.01 meter squared. All right, so what I'm going to get here is 3.6 times 10 to the negative 4 newtons. That's the magnitude of the force. Well, how about direction? Well, it depends on, right? So for example, if I'm considering this guy over here, QA, then the force is to the right. If I'm considering QB, then the force will be, to the left. So it depends. Let's say which charge I will be then considering. But remember, this equation gives you the magnitude, the strength, and then the direction you just basically get from the configuration itself and which charge is, let's say, charge of interest. Here's another example. You have two 1 kilogram masses are 1 meter apart on a frictionless table. Each has 1 microcoulomb of charge. So what is the magnitude of the electric force on one of the masses? Well, here's the picture of that. So because they are 1 meter apart, I can take the charge 1, Q1, and put it at the origin, and the Q2 just 1 meter apart from that. Because they're both positive, they're going to be repelling each other, right? So they're going to be a repulsive force between them. So I also have the charge, right? So that means what I have is Q1 equals Q2 equals 1 microcoulomb, which means it's 1 times 10 to the negative 6 coulomb. That's what micro stands for. We're also given their mass, which is 1 kilogram. Right. So remember, you don't really need mass if you're calculating the electric force. So if I'm calculating electric force, this is 2(1), which is same as 1(2), is K Q1 Q2 over R squared. All right. So one thing I want to mention that I want to go back actually to the previous example is I just noticed that I just made a mistake over there. So when we're calculating this example over here, see FAB, which is FBA, see what I have here is this, is 9 times 10 to the 9. Just because I wrote that, I can't get, distracted. So then times QA times QB. So remember, one of the things we do here is we use always absolute value because we're calculating the magnitude. So it's going to be an absolute value. See, QA is negative, but I'm just going to put this as 1 times 10 to the negative 6 coulomb. And then QB here is 4 times 10 to the, sorry, not negative 6, negative 9, because this is nano. Okay. And then this is divided by 0.01 meter square. Okay. Sorry about that. All right. So then what I have here is this. We are using always absolute value whenever we're calculating the magnitude of the force. So then this will be 3.6 times 10 to the negative 4 newtons. Okay. And what I have here is, remember, magnitude of a vector can never be negative. That means I cannot use the negative sign over here because then I'm going to get a negative number. But what I'm calculating here is magnitude, because the direction, again, you get from the configuration. See, this is to the, it's a negative charge. The other one is positive, so they're attracted. That means negative charge has to be, pulled toward the positive charge. Same thing with the positive charge. The force on positive charge is toward the negative charge. That means it has to be negative, to the left in this case. All right, so let's continue here. So if I'm calculating this, then I can say, all right, so it's K, which is 9 times 10 to the negative 9. Keep doing that. Newton meter square over Coulomb square. Then times, well, see here, I can do this. It's K, since Q1 is Q2 equal, right? I can just say Q, and here just put Q square. I can do that because they both are identical. So then I can say then it's 1 times 10 to the negative 6 Coulomb square. And then this is divided by their separation, which is 1 meter squared. All right, so what are we going to get? So we're going to get then 9 times 10 to the negative 3 newtons. That's the magnitude of the force between them. That's the magnitude of the force between those two charged particles. All right, so there's also part B, which says, all right, so what is the initial acceleration of each mass if they are released and allowed to move? Because think like that. Right now, if you're holding Q1 and Q2, because they're charged, they exert force on one another. That means as soon as I let them go, the force is gonna, acting on those charges, and they're gonna make them accelerate. So let's say Q1 gonna accelerate to the left, Q2 gonna accelerate to the right. So let's say in this case, what is the initial acceleration of each mass? Well, because they have the same charge, because they have the same mass, well, both of them are 1 kilogram, right? Because they have the same force, this acceleration of 1 is same as acceleration of 2. And that's going to be, how do I find acceleration? Well, remember, Newton's second law, right? So net force divided by the mass. So that means acceleration is equals to force. In this case, happened to be just one electric force over the mass, which is mass of a, object right here, this particle. So it's 9 times 10 to the negative 3 newtons divided by 1 kilogram. So this is 9 times 10 to the negative 3 meter per second square. And that's the magnitude of the acceleration. Now this Q2 going to accelerate to the right, Q1 going to accelerate to the left. You have two different direction accelerations, but still, what you have here is you have acceleration that depends on the force. Well, one thing I want to also make it clear here is this. See, this force is when they are separating by this distance. So what happens when, let's say, they move, I don't know, let's say 2 meters apart? What will be the force between them? Well, I can calculate that, right? I can calculate, which is I put here 2 square, which make it 4. That means technically is 9 over 4 times 10 to the negative 3 newtons. You can see, right, it's 1/4 of that. Let's say, which is roughly, I don't know what, like, 2 point something, right? 2.1, 2.2, let's say. 2.25, right, actually. So it's weaker force. How about acceleration? Well, you still have acceleration because you have a force, but still, because, the force is weaker, acceleration is weaker. Does it mean that object is slowing down? Of course not, because there's still acceleration in the direction of its motion, right? So let's say if this guy is speeding up to the right, remember, acceleration means you're increasing your speed. Well, now the force is decreasing because it's moving apart from one another. More you move apart, weaker the force. But still, there is a force that's pushing you in that direction. Weaker or not, it still gives you acceleration. And acceleration too, weaker, it is weaker than before, but it's still, you have acceleration in the same direction as before. That means you still continue speeding up. Okay, so this is not a constant force. Electric force is not a constant force in this case. It changes with position, which means acceleration changes with position. But still, because you have a force that's always going to be pointing in that direction, even though it gets weaker and weaker and weaker, but it's still pointing in that direction, you're going to be speeding up in that direction. You're going to speeding up at a lower rate, but you will always going to be speeding up until pretty much all the way to infinity. All right. All right, so here's one more example here. So I have like a couple of examples here that kind of demonstrate different type of, let's say, problems. So how to convert from some kind of charge to number of particles, how to deal with, let's say, two particles and things like that when they have a force between them. So here's, we have a small plastic sphere with a charge of -5 nanocoulomb is near another plastic sphere with a charge of -12 nanocoulomb. I have different charges, both of them negative. Now, so let's say you can do, here's one. So you can say, Q1 equals -5 nanocoulomb. And here's two, you can make it a little bit bigger. Q2 is equals -12 nanocoulomb. Says if the spheres, and let's say, remember they're, let's say separated by distance r. So if the spheres repel one another with a force of magnitude 8.2 times 10 to the -4 Newton, what is the distance between them? All right, that means right now we're given the charge. We are told that they're going to repel, and they're going to repel because they're in opposite, they're same charge. So their force is going to be in opposite direction. They're going to repel. But we're given the magnitude of that force, 8.2 times 10 to the -4 newtons. Same is here. So it's a force magnitude as 8.2 times 10 to the -4 newtons. But that means if they have this charge, if the force between them has that magnitude, how far apart are they? That means what I have here is I'm using this equation where K Q1 Q2 over R square, and we're using absolute value. But in this case, I'm given everything but R. So what you need to do here is you need to rearrange this. So you can kind of like cross multiply, move R square here. So then divide both sides by the force. So then R square is equals to K, Q1, Q2 over the force, and then take the square root of both sides. So then R is equals to square root of 9 times 10 to the 9, that's 4K. And then 5 times 10 to the -9 coulomb. Remember, absolute value, it means, you don't put the negative. 12 times 10 to the -9 coulomb, again, absolute value. Then divided by the force, which is 8.2 times 10 to the -4 newtons. All right, so if I calculate, I'm going to get a distance between those to be 0.026 meters, or you can say it's 2.6 centimeters. That means only when they are 2.6 centimeters apart, you will have that magnitude of force acting on them. All right. Here's one more example. You have now 3-point charges. Okay, so we're kind of getting a little more, increasing kind of like difficulty. So there are now 3-point charges on the x-axis. So we have one charge, Q1, is -6 microcoulomb, and it's located at x equals -3 meters. So let's say, so this is the origin, right? This is the origin. So here's Q1. So it is located at x equals -3 meters. Q2, which is 4 microcoulomb, is at the origin. And Q3, which is -6 microcoulomb, is at x equals 3 meters. Now, whenever you're given 3 charges, then you have to understand, right? So technically then what I have here is those 3 charges, they all interact with one another, okay? That means there is an interaction between Q1 and Q2. There's interaction between Q1 and Q3. There's also interaction between Q3 and Q2. That means they pull and push and things like that on one another. But generally when we have this, we usually only look at one object of interest and concentrate on that object or on that charge, let's say. And you can see here, so it says, find the electric force on Q1. That means what I want here is, I want to see how the Q1 and Q2 and Q1 and Q3 are interacting. That means all the charges interacting with Q1, and I don't care about this because I don't care how Q2 and Q3 interacting. What I want to look at here is interaction with respect to Q1. And then you can see then what I have here is this. See, Q2 is a positive charge, right? So it's a positive charge. See, Q1 is a negative charge. Q3 is also a negative charge. Now, what I have here is this. Q1 and Q2, when Q1 and Q2 interact, because they're in opposite charges, right? They attract. Well, they attract each other because they have, opposite charges, right? Well, when then Q1 and Q3 interact, they repel each other. Okay, they repel each other. Now, what I have here is, so what I have here is then this. So thing like this. So if this is Q1, this is Q2, this is Q3, right? Then from the direction of the forces point of view, right? That means when I'm writing, when I'm doing basically free body diagram, and I say, all right, so here's my charge Q1, my charge of interest. Now Q1, when I'm looking at this interaction, Q1 and Q2, is going to be attracted. So here's the force. This is 2 exerting on 1. When I'm looking at this interaction, Q1, Q3, well, there's a repulsive interaction. Repulsive means that Q1 is being pushed by Q3, which means this will be then the force that 3 exerts on 1. And you can see, right, those forces are in opposite direction. That means what I can do here is I can see that what I'm dealing with is the net force. I need to calculate the net force, which is in a vector format, is the sum of F21 plus F31. That means I need to add those two as vectors. All right. Well, here you need to go back and remember how to deal with vectors. Okay. Now let's first look at in terms of the magnitude of this guy. So remember, one of the things I can do here is this. So the net force is equals to. All right. So one of the things we do here is in physics classes, sometimes we use unit vectors to represent direction. So let's say I can use what I call I hat. So like a hat, right? So I hat to represent X direction. And I can represent J hat to represent Y direction. So in this, let's say in this class, sometimes you might see me doing that. Because then what I can do here is this. See, this F21 is the magnitude of the force that, 2 exerts on 1. But because this force is horizontal, I can put this as I hat, because magnitude, direction. Then plus F31. Well, F31 is also horizontal, but I hat is positive X, because this is to the left, and I will put this as negative I hat. That means what I get here is this, F21 I hat minus F31 I hat. This minus goes here, okay. But what I have here is this. See, I'm adding two vectors, and you can see, right, because even though I'm subtracting, right, but because both of them are I hat, which means both of them are horizontal vectors, I can algebraically add them together. Remember your vectors, right? You can algebraically add two vectors together if they are on the same axis. And that's what I was verifying this. Because if I had extra, let's say like a vertical force or something like that, then I could not just algebraically add them together. But here I can. That means once I find magnitude of the F21, and then I find magnitude of F31, then I can just subtract them. Because what I get here is this. See, I can kind of factor out I hat and have this. Magnitude of F21 minus magnitude of F31, and that will give me the net force. And I will know that net force is also going to be horizontal. But the thing is, okay, so here's Q1. It's being pulled by Q2, being pushed by Q3. In which direction will it move? Well, it depends which force is stronger, and that's what we're going to find out when we do this calculation. All right, so let's do this calculation. So what is F21? Well, F21 is K Q2 Q1 over distance R12. Then minus, well, what is F31? Well, it's K Q3 Q1 divided by I31. That means the distance between charge 1 and 3. Then I hat is just their direction. All right, so one thing I can also do here is maybe simplify a little bit. You can see, right, I can factor out a little bit. I try to always do this. Whenever I can, make the calculation a little bit easier, I do that. See, both of them had K and both of them had Q1. So in a way, I can factor those two out. So K, Q1, then times that in the parentheses. That means it's 9 times 10 to the negative 9, which is 4K. Then Q1 is that guy, remember, again, positive, right? Absolute value. 6 times 10 to the negative 6 Coulomb. Then I have what's in the parentheses. Oh, remember, that's R square. Let's not forget those. Sorry. So Q2 is 4 microcoulomb. So 4 times 10 to the negative 6 Coulomb divided by distance between 1 and 2. That's this distance. And we can see that Q2 is at the origin, Q1 negative 3. That means this is 3 meters square. Then minus Q3 is negative 6 microcoulomb. So 6 times, again, you don't put the negative 6 for the 6. So just 6 times 10 to the negative 6 Coulomb divided by the separation between 1 and 3. And that's this distance, which is 3 and 3, right? Then it's 6 meters square. I have. And when we do that, we're going to get the magnitude. If we do the calculation, we're going to get 1.5 times 10 to the negative 2 newtons. All right, and it's going to be, we're going to get positive here, I hat. So it's a positive. Positive I hat means then overall, then the force acting on charge Q1. Let's do it maybe that color. So overall, the force then will be in this direction. This is the net force. That means charge 1 can be pulled to the right. Now let's see why. See, technically Q2 is less, right? It's a smaller magnitude than Q3. Q3 is much stronger technically in terms of its charge. But see, the distance, remember, is also a factor, and the factor is the distance squared. So even though the Q3 is stronger, Q2 is closer. So the force that Q2 exerts is much stronger, right? So that's why at the end, what we get is overall positive. That means attractive toward Q2 force. That means Q1 going to be attracted to that configuration. It's going to be then speeding up to the right. All right. Okay, so I have one last example here in electric force calculations. All right, so generally, this electric force calculation, as you can see, right, requires a lot of vector calculation. And what I'm doing here is probably one of the hardest one because this is now a two-dimensional vector calculation. All right, so if 2 electrons are each 1.5 times 10 to the negative 10 meter from a proton, as shown in the figure, right? Find the magnitude and direction of the net electrical force they will exert on the proton. Again, it's a combination of 3 charges. That means what we have here is they're all interacting, right? So I don't know, let's call this, so P, E1, and E2. That means what we have is that P interacting with E1, P interacting with E2, and so then technically then E1 interacting with E2. They also interact with one another. But because my charge of interest is a proton, that means I'm only looking at the interaction where it includes proton. So I ignore this interaction, and I'm only looking at those two. Proton, electron, attract, proton, electron, attract. That means I'm going to look at two attractive interaction. All right. Now, let's then, let me show you in terms of how I approach this type of calculation. Because see, one of the things we have here is that those two forces, right? When we look at those, that, you know, when the E2 and E1 exert force on the proton, so I get now a two-dimensional, you know, vectors. So what I do here is this. So I take then proton as my charge of interest, and I put the proton then at the center of my coordinate system. Right, so this is my proton. Okay, then what I have here is this. So here's, you can see right, here's the electron, E1. This is, you know, R1. And then let's say here's the, you know, second charge, E2. Okay, and let's say this is then R2, right? All right. And we're given that this is 65 degrees. Okay. Remember, what I'm interested here is net electrical force on the proton. That means I'm only looking at the forces acting on the proton. And then the forces that I have acting on the proton are going to be two attractive forces, right? Two attractive forces, one toward E1, another one toward E2. So let's see then. Here's going to be one force. So this is then F1 on the proton, right? Or let's call it just F1. And then here's going to be another force, and this is then F2. Because the proton has a force toward E1, because E1 is pulling, and there's another force toward E2. And what I have here is, you can see, right, F2 is a one-dimensional force on the x-axis, but F1 is a two-dimensional force. That means we have to here, you know, use what we call component method to calculate the net force. Now, in terms of the vector format, I still have this. Net force is equals to F1 plus F2. But I cannot just simply add them together because F2 is a horizontal, but F1 has components in both horizontal and vertical direction. So remember, if you have a force that is two-dimensional, what you do here is you find, and let's say here's the direction and here's the magnitude. What you do here is you find its x component, which, let's say if this is an adjacent side, becomes magnitude times cosine of theta, and then the y component, which then becomes f sine of theta. And that's what we're going to then do, because F1 has both x and y components. All right, so think like this. It's a three-step, you know, or four-step problem. Step one, do this, what we call free body diagram, right? So this is free body diagram. Step two would be then to make a table. So organize your vectors. So this table, so here I have my forces, and my forces are F1, and I have F2. And remember, when I add them together, I'm going to get net force F. But I cannot get net force F directly because F1 is, let's say, for example, is two-dimensional. That means what I need to do here is look at their components and try, what I can do here is try to get then the force, the net force component X and the net force component Y. That means find the component of the net force. That means here I need to do F1X, F1Y, F2X, F2Y. Okay, so kind of like this is the table that you're going to be making. Right. Now let's see what F1X is. Well, here so F1X, that means the X component of this force 1, and because then the force 1 is, let's say, kind of similar to this, right? It's the direction is given with respect to positive X axis. I can write this as F1 cosine of 65. Then F1Y then becomes F1 sine of 65. Now, then you remember that this vector F1 is in the first quadrant, and for the first quadrant, X component positive, Y component positive. So you put positive, positive. All right, so then for the F2, when you look at the components, then you can see, right, then F2 has horizontal, let's say component, but not vertical component. That means here is 0, and all the force by itself is in the X direction. And that's what we have. That means the way I need to then do the calculation is this. Take then this column and use it to calculate. So let's say this is, you see, this is the step 2, right? The step 2 is the table. Then step 3. Step 3 will be the calculation of the net force in the X direction, which will be then sum of the X components. That means it's F1 cosine of 65 plus F2. And so this gives me my equation 1, and equation 2 will be net force in the Y direction. And that will be, basically in Y direction, I have just F sine of 65. Okay. All right, let's calculate the X direction force, or the component of the net force. So what is F1? Well, F1 is the force between a proton and electron 1. So there will be K. Remember, what is electron? So let's say K. What is the proton charge? It is just E. What is the electron charge? Is also E. Remember, we're doing the absolute value, right? So it's E times E. So technically I can just put this as E squared. Then divided by the distance between them squared. But then also then cosine of 65. Then plus, then F2. What is F2? Is the force between charge, a proton and electron 2. So it's K times E proton, E electron. But again, I can just put this as E squared, because remember, if I'm doing Q for proton is E. If I'm doing Q for electron is also E. The difference here is plus or minus, but because we're using absolute value, is the same. Excuse me. And then this is divided by R2 squared. Okay, so this is basically what I have. All right, so then what I get from here is this. So let me kind of do the calculation here. So I can see that, I can pretty much factor out KE squared, right? And what I get here is cosine of 65 over R squared, R1 squared, plus 1 over R2 squared. Okay. Now remember, R1 equals R2 equals 1.5 times 10 to the negative 10 meters, because we're given each one have the same distance. Okay. And cosine is basically angle given, right? 65. So what I have here is this then. 9 times 10 to the 9, that's for K. Then 1.6 times 10 to the negative 19, that's for E, and then I'm squaring that. Then cosine of 65 divided by then distance, 1.5 times 10 to the negative 10 meters square, then plus 1 over, technically I could have even factored that one out. 1.5 times 10 to the negative 10 meters squared. So I get that. All right, so what do we get at the end? Well, let me see. I can come back and clean this up a little bit over here so I have room. Let me see if I give myself room over there. Okay, we could have actually used this one here. Anyway, so again, so, oops. Net force in the x direction, right? So what I did here is k e square, then I did cosine of 65 over r1 square plus 1 over r2 squared, right? Again, I could have factored out r1 and r2 the same because they're the same, right? But in any case, if I do this calculation, which, plug in the numbers, I can then get for the x component 1.46 times 10 to the negative 8 newtons. Same way if I do the net force in the y direction, which will be k e square. Remember, this is just f, sorry, just f, f1 sine of 65, right? This is just the y component of the force f1. So then this is k e square over r1 square and sine of 65. So 9 times 10 to the negative 9, 1.6 times 10 to the negative 19 squared, divided by 1.5 times 10 to the negative 10 meters squared, then sine of 65. Then net force in the y direction would be 9.27 times 10 to the negative 9 newtons. That means our goal from that force table to get those two equations. That means, remember, this is step 3, where we get 2 equations. And those are our 2 equations, which is the columns in that table. Because when you're dealing with component vectors, you need to use this approach. You need to find, let's say, the x and y component of the net force. Because once I have that, here's a step 4, then I can use the Pythagorean theorem, because components of any force, I can use then Pythagorean theorem to calculate then the magnitude of the force, because it will be net force in the x square plus net force in the y direction square. So 1.46 times 10 to the negative 8 Newton square plus 9.27 times 10 to the negative 9 Newton squared. Then magnitude will be equals to 1.73 times 10 to the negative 8 newtons. That means that's the strength of the force that proton will have, exerted. But what will be the direction of this force? Because remember, so here's our proton, it's being pulled in this direction and in that direction. So in which direction will it move? If you remember the graphical method of the vector addition, hopefully you guys can see that if I construct a parallelogram, the force will technically be in that direction. That's the direction of the net force. But I can find that precisely by using tangent of theta of net force in the y direction of the net force in the x direction. Or theta here is equals to inverse tangent of y component, 9.27 times 10 to the negative 9 newtons, divided by x component, 1.46 times 10 to the negative 8 newtons. And this should give me 32.4 degrees, which matches, remember, this was 65. So this is about half of that, roughly 32. That means this is where the proton will be actually speeding up, right through the middle of those 2 electrons. Because when you pull from both sides, you go basically in the direction of the net effect. And the force magnitude has that, and direction is that. Right.